Okay, yeah, I think we can start with the first talk, which I will be presenting, and I am going to cover the basics of HIP and ROCm. So welcome everybody for the second day of training. This is going to be an exciting day, as much as yesterday. And we're very happy to have everyone here, and we are ready to dive in once again. So just a quick second to acknowledge the work of my team members for getting this content ready. It's really a team effort, and our team is very good at producing this type of content and delivering trainings across the world. So just 1 second to give them the credit that they deserve. Okay, so this is the agenda for this talk. We are going to discuss some basics of AMD GPU programming. If you are familiar with CUDA, you may have already heard some of this, but obviously I am going to discuss how these concepts translate and apply to AMD GPUs. Next, I am going to discuss the most popular or most frequently used HIP API calls and how to write GPU kernel code. Then we are going to discuss device management and how to work with asynchronous computing. We're going to briefly touch upon shared memory and thread synchronization, and then I'll show you some details on ROCm and ROCm libraries. Okay, so off with the first topic. As I said, if you are familiar with CUDA already, you may have already heard about the concept of a grid of threads. So when you are running a kernel on an AMD GPU, as well as on an NVIDIA GPU, the execution is carried out by threads, which are the basic units of computation that will execute the work for you. These threads can be thought of as existing on a grid, much like if you're an application person, a mesh. And this grid can be a 1D, 2D, or 3D. The grid is partitioned into equal-sized blocks of threads, and each block is made up of multiple threads. So if you take a look at that picture on the right, you start from the grid, which is composed of blocks. Each block is composed of threads. And even though this grid is not really existing in your hardware, you can still query information from the grid to use in the software when you're gonna write your kernel. So just a quick comparison between the AMD and NVIDIA terminology. Both AMD and NVIDIA call the grid and the threads. Although the NVIDIA block is referred to as work group for AMD. And the most important difference is that the warp size for NVIDIA is 32 threads, whereas for AMD, the wavefront has size of 64 threads. So that's the most important difference to be aware of. So in terms of querying the information of the grid, threads in the grid have access to, for instance, their respective block or work group, according to AMD's terminology, which can be obtained by using this syntax here, block id.x, if we're assuming we're on a 1D grid for now, for simplicity. You can obtain the thread ID within the block, so locally with thread ID .x. You can also get the block's dimension, so the number of threads in the block, with blockdim.x, and then eventually the grid's dimension, so the number of blocks or work groups in the grid with griddim.x. So this picture here is just the simple schematics of how a 1D thread grid would look like. And we have different blocks that are marked with different colors, so blue or orange, and each block is composed of 4 threads in this picture, and the blocks make up your 1D grid. So for instance, you could obtain the global ID of a given thread in the grid by using the information that excuse me, we have just introduced. For instance, this int ID could be the global thread ID of the thread 3 of block 2. So basically, we can obtain the global ID with this operation here, where we have that the block dimension is 4, meaning that we have 4 threads in the block. The block ID is 2 if we are considering the thread which has ID 3 locally on block 2. And then, as I said, it has local ID 3. So we would do 4 times 2 plus 3, and that would be 11, the global ID. So basically from here, if you can see my cursor, we're just counting from 0 to 11. And that's what identifies this thread globally. And as I mentioned, the grid can be 1D, 2D, or 3D. So in the case of a 2D grid, you can get similar information as what we have already discussed, but instead of doing the .x, you would be doing the .y. So you can get the respective block IDs by doing block ID.x or block ID.y, for instance, depending on whether you're going on the x or on the y dimension. And this can be generalized to the 3D case as well. So if your problem has higher dimensionality than just 3, you're going to have to find a way to map it to a lower dimensional case. But it's common that a 1D grid might just do it for you. If not, you can resort to 2D or 3D. Okay, so let's take a look at the HIP API now and how to write GPU kernels. Okay, so first of all, for those of you that are not already familiar with HIP or that have mostly worked with CUDA, HIP is short for Heterogeneous Compute Interface for Portability, and it's AMD's C++ runtime API and kernel language, which you would be using to program AMD GPUs. And it's open source, as you may already be aware of, and has very similar API calls as CUDA. And in fact, most of the CUDA API calls are also available in HIP. And the idea of HIP, as the name suggests, is to foster portability, because if you are going to program your code with HIP, then you will be able to run on either AMD or NVIDIA GPUs. So your code will work for either one, and depending on whether you are running on AMD or NVIDIA hardware, the specific GPU and compilers will be detected, but that will be already taken care of for you. So these are some of the API calls that we're going to be discussing in this presentation. For your reference, at the top, there is a link that contains a lot more than the ones that are just displayed here. What's relevant specifically for this talk is um, allocation calls for memory management, string creation and synchronization calls, and also some calls for error handling, which are intended to uh, debug errors that may be occurring at runtime, synchronization errors like associated with kernels, and also API calls errors. We'll dive deep into those next. Okay, so let's just take a look at how a snippet of code would be for a simple GPU multiply considering a discrete GPU such as the one you have available on Archer 2. So first of all, we have to include the heap runtime header, which is here, heap runtime.h. And then we have the GPU kernel definition. So this is just a simple kernel that would take an array and basically multiply each entry of this array by 2. So I would like to direct your attention to this int ID definition here, which is exactly what we have discussed in the previous slide with the 1D grid. And you see that we are basically using the global thread ID to go ahead and modify the entries of the array. Because in case you're not familiar already with GPU programming and kernels, you have to think that when you are launching a GPU kernel, all the threads that you are initiating will execute at the same time. And your goal is to use these threads to do the computations that you need, leveraging how many threads you have defined in your grid. So this is the simplest case where basically each thread is doing just one operation, this multiplication by 2. But you can do more complex operations with striding, for instance, when a thread is actually reused to do just more than one operation. This is just the simplest case that I'm showing you. The next thing that I'd like you to pay attention to is the allocation and initialization of a host memory buffer, which is done just with the simple malloc. And the host buffer in this code snippet will start with an H. And remember from yesterday that host means CPU and device means GPU. Okay, so we are setting ourselves in the framework of a discrete GPU. Therefore, what we are doing next is we are also allocating memory directly on the device with the heap malloc call. And we are using the device pointer d_a. And then we are copying the memory that we have initialized on the host array h_a into the device one. You see here we have heap mem copy host to device. So this is not needed for the APU for the MI300A that you have available on AAC, as we have already seen yesterday. Next, we are, is there a question?
Yes, I've got a question about that. The last slide.
I'm sorry, let me go back.
So on
This
the
one?
right-hand side, you're claiming you don't need the mem copy, but then your kernel invocation is still using the DA. Is this?
Yeah, yes. No, yeah. So if you were on MI300A, then you would feed the HA to the
You
kernel.
need the host point,
Correct.
right? Okay, yeah.
Yes. Thank you. Yeah, that's a good observation. Yeah, so the next thing to do is to actually create the thread grid by specifying the number of threads per block and the number of blocks in the grid. So you see that, and this is a bit of a tricky point that I think sometimes it's a little bit looked over, but the important thing is that you have enough threads to do the computation that you need to do. It's one of the important things. So when you define your thread grid, you have to make sure that this happens. And in this case, you see that this blocks in grid definition is using the size of the array, which is capital N. So in this way, we are making sure that we have enough threads. We may have more than we need, but the important thing is that we have enough to make our computation. And then we are launching the multiply kernel, which is getting as arguments the array and the size of the array, as well as the grid dimension. And then there's another step that's needed for the discrete GPU, but not for the APU, which is the copy back from the device buffer to the host buffer, and then we are freeing the device memory. Okay, yeah, so just giving a little bit more extra focus to what we have seen right now. With a discrete GPU, for better performance, it's advised to do explicit memory management. We've seen yesterday that we can mimic the APU programming model on the discrete GPU with an appropriate environment variable, but for discrete GPU, for better performance, explicit memory management is recommended. And in this slide, I'm just basically highlighting these specific steps for the explicit management of memory, which are allocation on device, copy from host to device, some computation, and then copy back from device to host and freeing the memory. So looking specifically at the kernel, we can compare a simple CPU implementation on the top right of the slide with our implementation for the GPU over here. I think that something that immediately catches your eye is that for the CPU implementation, you have a for loop, and you are basically going through the indices of the array sequentially. But you have to think that for the GPU case, all the threads exist at the same time and are ideally executing the same operation at the same time. And obviously, this is going to create a different set of problems that in part we're going to be addressing in the next slides. But the important thing to be aware in this specific case is that since the global ID of your thread may be more than the dimension of the array because of the way we have defined the grid, we have to be careful not to go out of bounds in the array addressing, and therefore we need to have this if condition here to make sure that ID is not bigger than the size of the array. And we are going to discuss next what this global declaration here means for the kernel. And the other thing to be aware of is that GPU kernels have to be declared as void, so they do not have a return value. Yes, so this slide over here basically shows you what are the arguments for the kernel launch, and we have seen blocks in grid and threads per block, and these are usually objects of type DIM3, because in general, the grid can be up to 3-dimensional. But we also have two optional arguments that are the bytes of shared memory and also the stream ID. We're going to discuss them next in this presentation. Okay, so the other thing to talk about is the software to hardware mapping, and I'm going to try to present you a justification as to why we have this thread grid and why it sort of makes sense to use it, considering the type of hardware that we have. So over here, I'm showing you a little diagram of a compute unit for an MI200 series AMD accelerator. And what we have to be aware of is that threads within the same workgroup or block execute on the same compute unit in chunks of 64 threads that are called wavefronts, which are the AMD equivalent of warps for NVIDIA. And remember that NVIDIA has 32 as size and AMD has 64. So these wavefronts share local data share memory, or LDS, which is that purple rectangle that you see in the drawing, and also L1 cache, and can synchronize. So the fact that they can synchronize can be leveraged to use shared memory and make your computation faster, basically. But in order to facilitate that, it's good practice to make the block size a multiple of 64, since threads in the block execute in chunks of 64 in the CU. And yeah, wavefront execute on SIMD units, which are the red rectangles in the drawing. And if a wavefront stalls, the CU can quickly context switch, which means that they can hide latency, provided that the resources of the GPU are used enough. It means that if you have to be using enough threads for this latency hiding to happen. Okay, so next, let's take a look at ROCm for a second. So ROCm is an open source platform for GPU computing, and it's basically what is used down the heap layer to work on AMD GPUs, and it's powered by AMD heap programming environment and runtime, and offers a wide variety of optimized libraries for GPU computing. So just a quick note about the latest ROCm release, which is 6.2.1, but starting from ROCm 6.2.0, the OmniTrace and OmniPerf tools are actually included with ROCm, whereas before, as they were part of AMD research work, they had to be installed separately. So now they kind of still have to be installed separately, but you can just do it with an apt-get install, and those will automatically appear into the ROCm directory. So specifically for this training, if you go on the AAC node that we have made available for you, you'll see that we have both modules for the OmniTrace and OmniPerf included in ROCm, and those that come out of AMD research. But we recommend that specifically for OmniPerf, you use version 6.2.1 for this training. Okay, so just taking a look at the ROCm GPU libraries, as we said, HIP is the layer for portability, which sits basically on top of the ROCm or the CUDA layers. And it's a thin layer, so it doesn't provide too much of an overhead. But the whole idea, as we already said, is to provide portability. So if you use HIP, then you'll be able to run on either NVIDIA or AMD GPUs. So now the question is, you have the option of using HIP libraries or ROC libraries. Which one should you use? So that depends on the purpose of your code in terms of where it's supposed to run. If you are interested in portability, so you know that you will run your code on different hardwares, then you should be using HIP library calls. However, if you know that you are going to prioritize almost exclusively AMD GPUs, then you should use ROC library calls, because they have some optimizations that are specific for AMD hardware. Yeah, so in terms of the ROC libraries, as you can see from this slide, there are AMD equivalent to NVIDIA libraries such as cuBLAS. We have ROCBLAS. cuFFT for the fast Fourier transform, we have ROCFFT, and so on. And these are optimized for AMD GPUs. And obviously there's more, but you can check the full list at this link down here that I have just updated for you yesterday. Okay, so if we take just BLAS as an example, ROCBLAS can be installed with just apt-get install. And as most of our code, it's open source, so you can find the source code on GitHub under ROCm/ROCBLAS. And this is where you'll find the documentation. And as I said, you should be using ROCBLAS if you are looking for ad hoc performance on AMD devices. On the other hand, HIP-BLAS is also open source and it's available on GitHub. And you should prioritize using HIP-BLAS if you are looking for portability, just as we already said. Okay, so with ROCm, you can also query your system and get information from your system. And I recommend you try some of these commands on our node, just to familiarize with them and see what kind of input you're gonna get. So with ROCm info, you can get a variety of information. We've seen yesterday that you can use it to find whether XNAC is enabled. You can also use it to find what type of hardware you are running on. If you grab on MI, all caps, it will tell you what GPU you are going to be running on. You can also find the version of ROCm. If you just cat this .info/version dev to terminal, it'll tell you the version. And you could also use ROCm SMI to get even more information that are more specific to the hardware, such as frequencies, power usage, and fan speeds, for instance. You could also change the power limits of your GPUs, though unfortunately you need sudo access for that. Okay, so the next thing that it's worth talking about is how can we handle error checking and device management, and also we should say something about asynchronous computing. Okay, so there are two types of heap errors that we can look for. The first one, which is also probably the easier to keep track of, is the type of error that's associated to API calls. And we can do that by basically checking the heap error status of every call. So we're gonna create a macro and then basically put it around every heap API call. For kernels, it's a little bit trickier because, as we said, they do not have a return value, so we just have to be a little more careful with those. So just let's see how we do that. Okay, yeah, so concerning API errors, we're going to be checking the heap error underscore t value for pretty much all the heap calls that we want, just by using this macro here that we call just like, GPU check. And then when we are calling heap malloc, that's going to happen as an argument of GPU check. So if anything wrong happens with heap malloc, then we're going to get an error message. And some of the examples in the exercise repo do have the macro, so you can see that in action if you want to experiment with that. Okay, yeah, so for what concerns checking kernels, as they don't have a return value, as we said, we have to be a little more careful and also think about what type of different errors we can incur on. For instance, we can differentiate between synchronous errors and asynchronous errors. The first kind, so synchronous errors, is associated with kernel launching, which maybe give you an error if you are providing, for instance, invalid execution parameters. And to monitor that, we can use the API call heap get last error. And also that's going to be inside the GPU check macro that we just discussed. For what concerns the asynchronous errors that happen during kernel execution, we should make use of synchronization calls such as heap device synchronize and also use the macro. So basically, heap get last error is gonna catch the launch errors, and heap device synchronize is supposed to catch the execution errors. Just be aware that synchronization barriers are good for debugging, but they can really slow down your code if you're trying to get good performance. So just be mindful that if you are seeing slowdowns that you don't expect, maybe it's because you are including too many synchronization barriers in your code. Okay, so something else to be aware of is the concept of non-blocking and blocking API calls. Non-blocking meaning for the host. So a call that is blocking for the host means that the host will not do anything until the call has finished, basically, until the work initiated by the call is finished. Non-blocking means that the host is gonna call that function and then just move on with new activity, basically. So launching a kernel is non-blocking for the host, meaning that after the host has launched the kernel, it's gonna continue with what's next on the to-do list. However, memory copies such as heap mem copy are blocking for the host. So until the mem copy has finished, the host is not going to do anything. However, it's possible to make asynchronous copies that actually allow the host to move on and not have to wait. So for that, we need to allocate non-pageable or pin memory for the host using heap host malloc. And then the asynchronous copy will be made possible with the heap memcopy async API call. Yeah, so for what concerns discrete GPUs, using pin memory can be very beneficial if you are going to be doing frequent host to device and device to host switches. For MI300A with the APU, the benefits of using heap host malloc will be reduced compared to the discrete GPU, since the memory space is the same. Okay, so the next concept to discuss is that of streams. And you'll see next that these are what we use for the asynchronous copies, so that's why we talk about them. So a stream in heap is just a queue of tasks that could be kernel launches, kernel execution, mem copies, or in general, just an event. And the thing to be aware of is that tasks in a stream are completed in the order they are received. And streams can be created with this heap stream underscore t type, and then you have to actually call the API call to create them. And then you can destroy them once you're done with them. So I don't know if you remember, but a few slides ago, I showed you what parameters a kernel is taking in, which is the grid size, the bytes of shared memory, and also the stream ID. So if you do not specify anything for the stream ID, the default is going to be the stream 0 or the null stream. And the null stream is where all the blocking calls happen, basically. So no task on the null stream will begin until all previously enqueued tasks in all other streams have completed. And that's why the blocking calls like heap mem copy run on the null stream. But the null stream is not the only stream you can work with. So right now, I'm just showing you what happens if you willingly specify the null stream for all your kernels here. Since the tasks on the stream are executed in the order they're received, kernel 1 comes before kernel 2. So you see that in the null stream, we're going to have kernel 1 first, then 2, 3, and 4. However, if we define different streams than the null and feed those to our kernel, we can actually obtain simultaneous execution of our kernels in a way that they don't have to wait for each other, basically. So you see that simplifying, assuming that all kernels are taking the same time, which is not going to be the case in general, you see that each of these kernels is executing on its own stream, and therefore they don't have to wait for each other, and they can be executed in an asynchronous manner. Okay, so one more usage of streams that we can do is to obtain overlapping of kernel execution with data movement. And the good news is that AMD GPUs have separate engines for host-to-device mem copies, device-to-host mem copies, and compute kernels. And we can leverage this using streams by basically overlapping execution with mem copies. So to do that, we just need to use streams, as we have done right now. This slide over here just shows you once again what happens if you put everything on the null stream. So in this case, you would have that all the copies occur, then the kernel executions, and then the copies back to host from device. However, oh, and also please notice that, as in the kernel launching, the last argument for the memcopy async is the stream ID. If once again we define separate streams and then pass them to the copies and the kernels, we can achieve a situation where kernel execution overlaps with memcopy, as you see here, for instance, as my kernel 1 is executing on stream 1, stream 2 is making the host 2 device copy. And that can save you time. That's the purpose of doing it. And once again, this is just a simplification where everything takes the same time, but in general, mem copies will take more time than your kernels. Okay, so how do we coordinate the execution of device streams with host execution? As we have seen already, we are going to take care of that with synchronization barriers, synchronization points. So the strongest of these is the hip device synchronize call, which basically blocks everything on the host until all work in all device streams has been completed. So this, as you can imagine, is the toughest synchronization barrier that you can have, which in some cases you do need, but in other cases you should probably just use for debugging purposes, since it makes everything wait. Something a little softer is the hip stream synchronize, which, as you specify the stream, blocks the host until all the work in that specific stream has completed. So you don't have to wait for all the other streams to finish. You can also synchronize a stream with another stream, and for that you will need the concept of events, but unfortunately there's no time to touch upon that today, but information on that is provided at this link. Yeah, so in our exercises repo, we have a couple of examples on stream overlapping. Specifically here, I'm showing you something that you would obtain with the stream_overlap example. So please be patient, because the tool that will show you this picture is Omnitrace, and you will see that Friday. But this is just a quick preview of what you would be able to see on Omnitrace. These are 8 streams on which we are basically overlapping a copy from host to device, and then a computation of the kernel that's called cube, that we on purpose made more compute heavy than it should, so that we could see the big rectangle basically in the trace, and then there's the copy back from host to device. So please wait for Omnitrace on Friday to see that picture. Yeah, so something else that we can do with HIP is querying the device and basically finding out how many GPUs we have with this get device count. We can also set a specific GPU we want to work on with hip set device, and we can get some properties as well that may be of interest for us with hip get device properties. Okay, so briefly, I would like to say something about function qualifiers, because we have seen the global declaration used for the kernel. So function can be declared as global, as we've seen, and these are the entry points for the device code, which are called from the host. As we've seen yesterday, the device code has multiple entry points, and global functions are an example of that. You could have device functions that can be called from global or another device function, but cannot be called from host code. and they're not compiled into host code, so they're basically ignored during the host compilation. And I should mention that the heap compiler, heapcc, makes two compilation passes through the source code, one for the host and one for the device, and that's what motivates these distinctions. And then we can declare functions as host device, which can be called from global, device, and host functions. Yeah, so let's just say something about memory declarations in device code. So as a general rule, you should not be doing malloc within a kernel because that's gonna slow down your execution. And stack variables that are declared in device code are allocated in registers and are private to each thread. However, you can leverage shared memory, and as we have seen, threads in the same wavefront can see shared memory. They have the same LDS, and so yeah, so you can declare some memory as shared when you operate with your GPU kernel. And as we said, shared memory is accessible by all threads in the same block, which is crucial for the way you're gonna leverage that for your kernel implementation. But you have to know the size at compile time. So an example is provided here, where we have a kernel that's called reverse, which is basically taking an array as input and then reversing its entries and then giving that as the output. So over here, we are declaring it as global, but inside we are also declaring some shared memory, this array of doubles that's shared within the block. So you see that what we're doing is we are taking the local thread ID within the block, and then we are making a copy of the device array into this shared memory array. And then we are copying that back into the original array to reverse it. But something that's very important here, and we should spend some time mentioning it, is that before we can copy back the data, we have to make this sync threads call, which basically is gonna have all wavefronts wait until any of them can proceed to the next data movement. And this is because, as we said, threads are all executing at the same time, and so it may happen without this sync thread call that a thread is making this copy from DA to SA and then trying to access something from SA in the next line that has not yet been modified by another thread. And that obviously will produce a wrong result. So this synchronization thread here is necessary to make sure that you're getting the correct answer. Yeah, so just to give you a few more details about what that does, the sync threads blocks a wavefront from continuing until all the other wavefronts have reached that synchronization barrier. And it's best practice to avoid deadlocks by checking that all threads in the block execute the same sync thread instructions. And then there are a couple of other details that you should be aware of to effectively use this synchronization barrier. Okay, yeah, so this is it for the heap talk. As yesterday, I encourage you to get on AAC, and I assume you may have already cloned the exercises repo. And the exercises that are relevant to this talk sit in the heap directory, which has its own README with instructions on how to run the exercises. But the heap directory is pretty big, and it has several subdirectories that have their own READMEs. So I recommend you check them out too. And also, let me just say that in case you haven't noticed, the top level README in the exercises repo on GitHub has a bit of a table of contents that shows you basically where the code is located for each topic, and also where you can find the associated READMEs. So in case there's something that we are not going to be discussing in this training, or something specific that you're looking for, I recommend you check this top level README and see if what you're looking for is there. So yeah, so this is all for the HIP talk. I'm gonna be here available if you have questions, and obviously we'll be monitoring the chat channel as yesterday. And by the way, thank you all for being so active on the Mattermost chat. We really appreciate that. We are happy to interact with you, and hopefully we're gonna be doing that today as well. So yeah, I'll reconvene at 2:30 your time, since we have a break at 2:15, 15-minute break, and then I'll tell you something about how to port from CUDA to HIP. Thank you. Okay, yeah, let me start with the next presentation. Hopefully most people are back online. Yeah, so the next talk will cover strategies to port your CUDA code to HIP. Okay, yeah, once again, I'm gonna take a second to acknowledge the work and contributions of my teammates in getting this content ready for you. Okay, so what are we doing here? Well, so we start with the assumption that we are dealing with a code that is using the CUDA API, and we want to port it to HIP so that it can run on AMD GPUs as well as NVIDIA GPUs. So unfortunately, there is no approach such as one size fits all, because codes can be very different. They can be optimized, for instance, to run on specific hardware. They may make heavy use of external libraries, and they may have kernels that are simple or complex. And so there's really no just one approach to solve this problem. Let's call it problem. So, for instance, if we are in a case where the code is relatively simple and self-contained, it may be just possible to use some of the simplest and less painful hipification tools. By hipification, we just mean transitioning from CUDA API to HIP API. And I'll tell you what these tools are just next. But it's possible that the code is more complex and has some ad hoc optimization for the specific device. And in that case, it may be harder to use just out-of-the-box options. And an approach that combines manual rewrites with automatization may be the right path forward for that case. So in terms of what are the tools that can achieve automatic hipification, starting from the simplest one, we have Hipify Perl, which is basically a string replacement script that is going to detect what strings have the CUDA name in it and just replace them with HIP. And this is available in the ROCm bin directory. So if you have installed ROCm, Hippify Perl will just sit inside the bin directory, as will most of the other tools that I'm going to mention. So Hippify Perl is recommended for a quick scan of a project, just to somewhat have an idea of how the hippification process might work. And, you know, as we said before, if your code is somewhat self-contained and does not have too many ad hoc implementations, then Hippify Perl might just be the right tool for you. On the more robust side, what we can offer is the next tool, which is Hippify Clang. And Hippify Clang, as the name suggests, needs the Clang compiler. And you also need to specify the same includes that you would for Clang. So in terms of how to use these tools, as we said, they are located in the ROCm bin directory. And from the command line, it's rather easy to do that. You just call Hippify Perl and then give the CUDA call as argument, and then you just pipe the output to a new source code that will have the hippification included. And it will include the hip runtime call, the API translation, and the good thing is that the library calls, the CUDA library calls, will also be modified by this tool. For what concerns Hippify Clang, as we said, it needs the Clang compiler. It is also located in the bin directory of ROCm. And it's more robust in the sense that it's gonna give you more instructive error messages in case something is not working with the hippification. And this is just an example of how you would use it. You would still feed the CUDA code as argument, but then you need to also give the right includes as if you were compiling with Clang. Okay, so over here, I am just reporting some of the success stories of code hippification. And these examples here show a wide span of porting time variation willingly, because we want to give you an idea that it really depends on the code that you are working with. You could be, in a way, lucky and just be able to port your code in one afternoon, such as for the HACC code, or it may take a little longer, such as for CUDA, which took around 3 weeks. But this is just to show that it can be a process that depends on your code, but eventually it will work out. So for what concerns other hippification tools, other than Hippify Perl and Hippify Clang, we also have in the bin directory some recursive directory tools that basically aim at calling the scripts that I already mentioned, but recursively for all a certain set of files that sit in the directory from which you are calling them. So for instance, the source code for hip converting place -perl will look like this. And you can see that calls the findcode.sh script that recursively looks for files that have, say, the .cu extension and so on. So this is what you can see inside these recursive scripts. So a couple of things to be aware of when initiating the parting process, the heapification process, is that, first of all, none of the tools that I have discussed so far actually checks your code for errors, meaning that it's up to the developer to check that the heapification process went through correctly and there are no errors that resulted after that. Something that we hear happens rather often is that CUDA codes have the warp size hard-coded to 32. And therefore, when you to AMD GPUs, the weight size is 64. Therefore, first thing to do I think is make sure you know, and this is on the final work size so that you don't have to be about any hard code. Something else to be aware of that you having one-to-one the critical and keeping and one hand in line with the XSL 6. To be aware of is that the heapification process does not take care of changing the CMake or the make process for you. So that's also something that you are in charge of. On the other hand, as I mentioned, heapify Perl and heapify Clang can convert library calls, so cubless will become heapless. And CMake has some automatic setup tools that can support some heap related CMake flags. Something else that it's worth mentioning is the heapify approach, which is a rather convenient way of parting your code with basically no changes, so just out of the box. So this is a procedure where you include this header file here that's linked at the bottom of the slide, and we're showing a part of it with this screenshot that basically is going to intercept the CUDA calls, the CUDA API calls, and swap them on the fly with heap API calls. That's why it's called heapify. So if this works for you, then it means that you don't have to do any changes to your code, and see that in the header, we have in fact defined the warp size and set it to 64. On the other hand, for this to work, you obviously need to have a one-to-one correspondence between the CUDA calls and the heap calls, and obviously they also have to be listed here in the header. And therefore, the success of the procedure has to be evaluated on a case-by-case basis. However, when it works, set is just an out-of-box procedure for your code to work. Build system that you can leverage to compile your code seamlessly, depending on whether you AMD GPUs, ROCm, or NVIDIA GPUs. My audio?
Yeah. maybe you can switch off your camera to.
Yeah, let me try that.
Let's see if that. I also have some issues. I don't know what is happening, but let's see if that works better.
Yeah, I've seen a few people logging back in and out.
Yeah, I had to do the same. I don't know what happened, but yeah, now the audio is way better.
Okay. Okay, yeah, I apologize for that. Hopefully, you were still able to hear most of the content. Okay, yeah, so 3 pages, of course. Is this okay, Salim?
Yeah, I think there is when I got disconnected.
Oh, okay, perfect. Yeah, so this was just, okay, great. This was showing just how the converting place tools look like. And basically, they recursively look at the files that have a specific extension and then proceed with doing the heapification on those. So something to be aware of is a few gotchas that may happen during the heapification process. It's still not working. Yeah, hold on. Let me try to go out and then back in. I am sitting to my router now, so that should not be a problem. Just 1 second. Okay, yeah, hopefully it's better now. Juan, can you? Yeah, perfect. Yeah. Okay. Yeah. Let's try again. So yeah. So just quickly, the gotchas to be aware of are that heapification tools do not check the correctness of your code. So it's up to the developer to check that the heapification process did not introduce any errors. And also, we have heard that it happens quite often that the warp size for CUDA is hard-coded to 32, but we've seen that the wavefront for AMD has a size of 64. So just grab for 32 to make sure that it's not hard-coded. And then define this warp size as just the variable so that you don't have to hard code it. Yeah, so the good news is that Heapify Perl and Heapify Clang can convert library calls. So cuBLAS becomes HeapBLAS. And also CMake, starting from version 3.21, has some support and can be used to automatically set up compilation flags that are relevant to HIP. Another tool that's relevant. Yeah, sorry about the audio. I don't know what's happening. I'm basically next to my router right now. But what I want to mention is the Heapify header, which is this header that's showing here. This is just a screenshot of the link at the bottom that tended to basically reach the CUDA API calls with HIP API calls. Code, if there's one correspondence between the CUDA API calls and the can just out of the box, so you wouldn't have to make any modification. Although you need this correspondence to happen, and therefore, performance of this has to be evaluated on a case-by-case basis. Yeah, so let's just take a quick look at how to have a portable build system so that you can seamlessly run on AMD GPUs through ROCm or NVIDIA GPUs through CUDA. And we're going to take a look at Make and CMake just because they are allegedly the most popular build systems. Okay, so for what concerns an example of Makefile, I have highlighted the parts that are most relevant for this discussion. And in the Makefile, we can define the heap platform variable and set it as a default to AMD. And then when we actually proceed and make, we can overwrite that and set it to NVIDIA if we want to run on NVIDIA hardware. And you see that depending on the value of this heap platform, we can set different compile flags for the specific GPU we're going to be running on. Yeah, so when we want to run with CUDA, we still have to load the ROCm module because we still need the heap portability layer. And then when we go ahead and run the make command, we're gonna override the heap platform with NVIDIA so that the make system picks that up and sets the appropriate flags. For what concerns CMake, the process is a little bit more involved, and it starts with setting the GPU runtime to ROCm, for instance.
Alarm off.
And something else that's relevant for the CMake, and I'm not gonna go through all the details, but you have them in the slide, is setting the language with enable language to the desired GPU runtime. And yeah, so different flags can be set once again as in for the Makefile for the compiler, depending on what hardware we're going to be running on. And then similarly to what I showed you before for the Makefile, for CUDA we still have to load the ROCm module. And when we actually run the CMake command, we're gonna override the GPU runtime and specify CUDA. So it's similar to what we've seen for the Makefile, except that it's needed. Yeah. Architecture for which you wanna compile, and you can do that with these two variables here. So GFX is associated with an LLVM target, and you can see a list of all of these GFX models at this LLVM docs link. But specifically, if you are on a system and you want to find out what's the code associated with your specific architecture, you can find that with ROCm info. So right now, if you're on AAC and just run this command, it will tell you GFX 942, which is the GFX model for the MI300A. Yeah, and I think that we should give a brief mention to also Fortran and how to port Fortran code that's written in CUDA Fortran. So there is no heap equivalent of CUDA Fortran. So the strategy is to kind of proceed with 3 different steps. The first one of which would be to manually port CUDA Fortran code to heap kernels with a C-like syntax. Then you would need to wrap the kernel launch in a C function and then call the C function from Fortran using ISO-C bindings. And you can have more information on this procedure by checking the HipFort GitHub repo. And we also have a few examples in our exercises repo. So about that, once again, clone the exercise repo. And for hipification, we have 3 directories. One that's just about hipification using hipify Perl and Clang. We have one specifically for hipifly with the header. And then there's, I think, one or at most 2 examples for HipFort. But yeah, this is it for the porting presentation. I apologize for the connection issues. I don't really know what happened there. But yeah, hopefully you got most of it through. And you know, I'm always available for questions, and obviously we'll send you the slides as well, so you have those. There's a break in 5 minutes, but if you want, you can just keep continue working on the exercise. And oh, sorry, no, sorry. There's no break. The break is after the next presentation. In 5 minutes, we actually have the presentation by Johanna on OpenMP and HIP interoperability. So I'm gonna let her share her slides so she can get ready.
Hello, I'll do a quick audio check. Is everything working?
Yes.
Okay. So I hope my audio will not be chopped like Giacomo had at the end. So we give everyone a break of 4 or 5 minutes and then we continue? Or what's the plan?
Yeah, I think your talk is scheduled to start in 3 minutes, but you can, yeah, we have flexibility on that, so you can wait a little bit longer if you'd like.
Yeah, I was just asking if participants may need a longer break. I don't know when the last one was.
The last one was at 2:15 Scotland time, and now it's almost 3, so I think it's okay. We have a break
Okay.
after your presentation. Yeah.
Great. Yeah, I'm just uploading the slides.
Thank you.
So we're at the top of the hour. Can we continue?
Yes, take it away. Yeah, so Johanna, she already spoke yesterday, so I think we can just say that she's connecting from Munich, and she's a great colleague of ours who talked about OpenMP yesterday, and she's gonna give you more details today about HIP and OpenMP interoperability. Thank you, Johanna. Take it away.
Yeah. Hello again, everyone. Today I'll be talking about HIP and OpenMP interoperability. Originally, our colleague Bob Rowley was scheduled to present this, but unfortunately he lost his voice, so I'm his voice today. I hope I can present his talk well and yeah, can provide you with the same information as he can do. So, hello everyone. Welcome to the HIP and OpenMP interoperability talk, hopefully without interruptions now. So, whoops. The HIP and OpenMP interoperability, why do we want that? Why do we want to use it? So in my presentation, yesterday, I already told you, okay, the great thing about OpenMP is that it supports that you can call a low-level HIP kernel from OpenMP, that you can call HIP or ROCm libraries like ROCblast, ROCFFT, and so on. From an OpenMP application code, you can call OpenMP kernels also from a low-level HIP application code, so the other way around, that you call OpenMP from HIP. This is probably usually not the usual way, so we will not show it here, but it's very beneficial that you can call especially the ROCm libraries from an OpenMP parallelized code. So why would you use both HIP and OpenMP? That's also something I already mentioned yesterday, that the advantage is that you have OpenMP as a higher level and more portable language, and you can write it quite quickly, and that reduces also code maintenance because you have less lines of code to maintain. That's the one thing. And the other thing is that OpenMP is very portable for different platforms. So a best practice is that you may want to use OpenMP for very straightforward loops and use HIP for more complex kernels and where performance really matters and you can't tweak it out of OpenMP. So now we're focusing on our favorite SAXPY example again. So here we have the SAXPY called inside larger example. So we want to allocate the device memory for X and Y and specify the directions of the data transfer. And then we now want to assume that we want to implement the SAXPY kernel later on in a lower level language. And the compute 1 and 2, which are used before this call of SAXPY, are some functions which are running on the CPU. And you have to be careful. Compute 1 and compute 2 modify X and Y. So we have to be careful that we use OMP target update 2 for X and Y such that the SAXPY function gets the right data. Okay, so now how did the SAXPY function look like for OpenMP? This is what I and Shelby presented yesterday. You have pragma OMP target teams distribute parallel 4 in this function. And that's all you have to do to offload it to the GPU. So now we assume we have a more elaborate function than a simple SAXPY, which doesn't run well with OpenMP offload, and we need some features which are only available in HIP, something which is a bit more flexible, something like what Giacomo presented as the advantages of HIP. So now we want to replace the SAXPY by a HIP kernel. Okay, how does this HIP kernel look like? This is, again, mainly what Giacomo already presented. What is important to know is that we need device pointers for X and Y. And now we need a way to translate the host pointer that was met by OpenMP directives to get the associated device pointer. Okay, now we put everything together. On the top, you see the HIP kernel, like it was on the last slide. And this HIP kernel is called from the OpenMP code we see below. So the SAXPY function call is now replaced by SAXPY HIP. SAXPY HIP, you see it on the top. And what's important now is that this SAXPY HIP gets the correct device pointer, like I mentioned on the last slide. So for the compute 1 and compute 2, the pointers which are used are pointing to host memory. But for the SAXPY HIP, we want to run it on the device, so it needs device pointers. So we have to ensure it gets a device pointer by the pragma OMP target data use device pointer. Otherwise, on discrete GPUs, you will get a segmentation fault because it can't find the memory. Okay, another important thing is that now this HIP code has to be translated with HIPCC and the OpenMP code with AMD Clang. So how do we achieve that? We put it in different translation units in different files. So you have to be careful that you use 2 different compilers in the makefile, hipcc to compile the saxb hip file, and AMD Clang to compile the OpenMP code. So it is very important to have the hip code in a separate file from the OpenMP code and compile the hip code with hipcc while you compile the OpenMP code with AMD Clang. A trick to combine both in hip and OpenMP code in a single file is to use preprocessor directives and copy the source to a separate file before compiling. That's possible if you need that. But if you write a new code where you have a lot of kernels, I would recommend just put it in 2 different files, less confusion what happens in the makefile. You can later try an example how to do that. That's mainly what we have on the slides here too. So how does it look like when you don't have a discrete GPU, but like we have in this training, the MI300A and APU? On the APU, you don't have to care about mapping of data. That's something we already showed you yesterday. So we can leave out most of the OpenMP directives we have here for the simple example. Don't have to, especially we don't have to care about this use device pointer because all pointers are pointing to the same memory. You only have to be careful to use HSAX neg equals 1. So after removing the memory pragmas, the code is much more simple. So you have only the saxb hip call instead of the saxb call compared to the original OpenMP example. And yeah, so the APU is very beneficial also for OpenMP and hip interoperability. There's also the APU example in the training examples repository. You can later try this yourself and get some experience with it. Then you're probably also interested how to do that with Fortran. So Giacomo already mentioned there is no such thing like CUDA Fortran, but it is possible to call hip from Fortran too. So now we are assuming we want to call DGEM from a hip kernel, something like we want to use a library which is called ROCm. And DGEM is implemented in an optimized way in this ROCm library. So we want to call it from an OpenMP code. So we have use device pointer again, like in the C example. And now it gets a bit more involved, like with C, because we need Fortran to hip interfaces. So we now have not only the call in our OpenMP code, but we need, usually put it in a separate module, we need the interfaces to the C code. So everyone who already worked with ISO C bindings, because you want to call a C library, for example, this is just the same way. Okay, so then the C interface is there, and you can then call C in the other in another compilation unit. So that's important that this works like in the C example I showed before, that you call the kernel inside the interface like in the C example. Yes. So important is that you put those 2 parts in 2 different translation units. So you use for the Fortran code and the interface with the ISO C binding, you use, for example, TrayFDN or the AMD Flang new. You now have for this training in the AMD Flang beta drop module, and the hip code, everything with C goes in the second translation unit, and you use hipcc to compile that. So that's very similar to what you have in C. So again, for Fortran, the additional thing you need is the Fortran to HIP interface. So if you want to call a routine from ROCblast, so the library, you don't have to write all those interfaces yourself, but for the ROCm libraries, someone already did that for you, and you can just build HipFort and have all those interfaces available. When you write your own HIP kernels and want to call them in the Fortran code, you have to do all the effort with writing the interfaces yourself. But the most common application of calling HIP from Fortran is probably calling the ROCm libraries, because they are optimized for our hardware. So it's very beneficial that you can use HipFort for that. So there's also this Fortran example in our exercise repository, and you can later check out how it works. To sum it up, OpenMP and HIP can be used in the same code. C and HIP code has to be in different compilation units, and you have to compile the one part with HipCC and the other part with AMD Clang ++. You have to be careful that you use device pointer for discrete GPUs, or when you use HSAXNAC = 0 on MI300A. When you want to call HIP code with the AP programming model, that doesn't require all this memory movement, so that's very easy to do. In Fortran, you need the C bindings to call HIP code, but HipFort provides it already for you if you use ROCm libraries in your Fortran code. So now I hope you have an overview how you can call HIP code in C or Fortran and make use of libraries. So I think now we have some time for exercises, but if you have questions first, please feel free to ask them. In Zoom, I can't see the chat, so I don't know what your questions are, so please raise your voice if you have any questions.
Thank you, Johanna, and thanks a lot for being able to switch from a platform to another one. That took a lot of flexibility on your end, and we definitely appreciate that.
I got a second try. Maybe I made it a bit better in the second time. It's also great for me. Practice. Yeah, no. I hope everyone got the message, despite the switching between conference tools.
Yeah, but since again now everything was like the audio, video, everything was way better. So thanks. Also for the switch for switching quite quickly.
Are there any questions in the chat, or are we going to start with the exercises?
Yeah, I think we can start with the exercises, and anyone that has questions can just use the Mattermost channel as normal. I think there might be a couple of questions that we still need to answer there. Yeah, and the next talk is at 4:15 Edinburgh time, and it's gonna be by Gina.
So Gina needs the right link too, Ben. So if we stay with Zoom.
Yeah, I pointed her to it. Hopefully she'll see it. Yeah.
I just noticed that my animations in this presentation were not the right ones, because I originally shared the PDF and now I shared the PowerPoint. Maybe Gina has careful with that too.
Oh, and in case people have missed it, we now have a link for you to get the Flame release that we have put in the node. Let me just put it in the chat and pin it in case people wanna see it. Hi, everybody, welcome back. Yeah, and Gina, this is the first time that you officially joined the call. Do you want to spend a couple minutes maybe introducing yourself to the audience?
Yeah, let's do that. So hi everyone, I'm Gina Sitaraman, and I make this really small. I'm a performance engineer in the HPC Solutions and Performance Analysis group at AMD, the same group that all of your speakers are from. And so we get to do all the fun stuff, optimizing applications from scientists like you from around the world for our hardware, mostly GPUs, but also in some cases CPUs. So it's been a fun 4 years for me here at AMD. So and along the way, I have gathered some notes, and this presentation is kind of one of those filled with a lot of tips that I hope will add value to what you are trying to do.
And also, yeah, Gina, after the presentation, she's also going to take care of the wrap up for this session for today. So yeah, if you're ready, the floor is yours. Thank you.
Thank you. So, so I guess from yesterday and today, you've had a little introduction to the architecture of AMD GPUs, maybe a little bit about how the APU architecture looks like, and you learned about HIP, how to maybe port your existing CUDA code easily into HIP so that you can run on AMD GPUs. Now we're going to dive a little bit deeper. Here we want to see, okay, once you've written something in HIP, you've got some kernels. How do we optimize those further? Some of the concepts that we are going to discuss here are already familiar for you, but we've tried to make it interesting with information about AMD GPUs, some things that are not the same as what you might have seen in NVIDIA GPUs, right? So that's where we're going, and all of our materials is teamwork. A lot of people help to put these things together, so I'm very grateful for the people mentioned here, and it's the whole AMD team behind this effort. And in this talk, we will look at, okay, what are the major kernel performance limiters? And once we know those, how do we optimize for each of those different types of kernels? And then I added a slide on what you need to think about when you have MI300A available to you, right? So we know that GPUs are high throughput devices, so it is very, very important to expose enough parallelism in order to fully utilize all of the resources. There are so many resources, and if we do not fully utilize them, then we are not doing justice to that device, right? Otherwise, the device gets starved. And when we think about GPU kernels and what they may be limited by, these three things just come up in first. The most HPC codes are typically memory bound. And let's talk a little bit about arithmetic intensity, and then these performance limiters will make more sense. Arithmetic intensity is a ratio of how many arithmetic operations you do per byte moved. So if you're having a lot of operations, then your kernel becomes compute bound. But if you're moving a lot of data and not doing so much compute, then that kernel is typically memory bandwidth bound. So low arithmetic intensity would be memory bandwidth bound. And in those cases, you would see that in your GPU hardware, the memory units are the ones that are most saturated. In compute bound cases, it's the compute units. And in latency bound, neither of these, the memory units are not that saturated, compute units are not that very saturated. So you are slowed down because of latencies at various levels. So we're going to discuss all of these. and what to do in case your kernel is one of these types. And of course, there are other types of limiters as well as we go deeper and deeper, but in this talk, we will just cover the basics. It's an introductory talk. So when we have memory bandwidth bound kernels, the very first thing that we want to think about is, okay, we're moving a lot of data. How can we reduce that, right? So whatever data we move first, we would like to make sure that we do as much compute as possible. That's the first thing. Try to move less data, reuse data when possible. This point here talks about how you can think about your algorithm in such a way that you can reduce on the data that you move and reuse that data by all the threads in your thread blocks as much as possible. Now, moving data from, so we know that there is a memory hierarchy in GPUs. There are memories that are farther away, and there are those that are closer. So going to HBM costs order of few hundred cycles, whereas going to shared memory, LDS, it's in the order of tens of cycles. So if it is possible for you to stage your data in LDS or shared memory, and even better in registers, it's very, very quick. It doesn't even take, you can access them. That's the fastest place to store your data and access them from your compute cores. That is a better strategy. If your algorithm can tolerate lower precision data, if you do not have to use FP64, you can work with FP32 or even lower precision, then you may want to think about just that because you would move fewer bytes. Another optimization that we often use, we try to move more data per work item. That way we can improve on that streaming efficiency. And we're going to see an example of that in a couple of slides. Okay, and when we consider how we access data, if all the threads in your wavefront are accessing locations and addresses that eventually that can be coalesced into one cache line or a few cache lines, then that is the best way of accessing, because even if you ask for 4 bytes, you're going to get 64 bytes in MI200 GPUs. In MI300 GPUs, it's a 128 byte cache line. So it is best if one thread is requesting the 4 bytes, you're going to get, say, 128 bytes. It's best if all the threads in your wavefront are going to use the data that is available already in that cache line. If you're going to access in a strided manner, then you're going to load more cache lines and use only part of those cache lines, and that is not a very effective strategy. And you will see that in the OmniPerf talk that's coming later in this workshop. The other thing that we talked about is loading more data per work item. That the second point illustrates that. If you were to use vector data types such as float 4 or float 2, then you're loading more data with the same number of instructions. So you use fewer instructions. That way you amortize on the cost of index calculations. Index calculations are typically integer calculations, and those also require the same arithmetic logic units that you need for your compute work. So amortizing on that is a good idea. You can improve on data streaming efficiency. In some cases, if you know that whatever you're reading from HBM does not need to be reused, it may be better to load them as non-temporal loads. And what this does is it loads the data into L2 in the least recently used slot. So if there is something to be evicted, that data will be the first one to get evicted. Because it's going to be used just once, that's fine. And if there are other pieces of data that you're going to reuse again and again, it's better not to evict them from L2. And that's the reason non-temporal loads can sometimes be beneficial for you. And aligning memory accesses, of course, can help you load fewer cache lines, the most efficient number of cache lines and not more. That gives a very slight improvement in performance, but that's something to have in mind. So in this example, here at the bottom, you can see there is a link. This is a link to Godbolt. It is a compiler explorer, which I'm a big fan of. So whenever we write our kernels, you can specify what compiler you want that to be compiled with, and it shows the assembly here. So here are two kernels. In the first kernel, there is each thread is going to load one element and write one element, right? It's a copy. If you were to write the same kernel where each thread loads two elements and writes two elements, the compiler somehow figures out that each thread is loading two contiguous elements in memory and converts that into a global load dword x2 instead of a dword. So this is a wider load. In one instruction, you're getting two FP32 values, and that's what we are aiming for. So sometimes the compiler does some work for you for free. You just need to know that and how to look for that. You can use Godbolt for this. You can use, when you compile, you can use save temps to get the ISA and look at the ISA for your kernels as well. ISA is nothing but assembly. Okay, so when we look at compute-bound kernels do a lot more computation. So, okay, we are doing a lot of compute. How do we reduce that? Is it possible to reduce that, right? That's what we are thinking. And in some cases, it may be beneficial to pre-compute values and store them in HBM and look them up than actually doing all of the calculations. Very few cases that is true. In some cases, using faster math intrinsic instructions can be beneficial because they take fewer instructions to implement an approximation, which may be perfectly fine for your use case. And a list of all those are given in this link in the ROCm documentation. In some cases, certain general math functions, like here, the power of a and a power 3 can be just two multiplications. Whereas if you were to go to this Godbolt link and see, it generates few hundred instructions for just doing the power function. So definitely these are things to look out for and avoid. You can, in CDNA2 and CDNA3, that is MI200 and MI300 architectures, you also have what are called packed operations. So two FP32 values are packed into one, an operation such as an add or a move can operate on two FP32 operations at the same time. So how you can get that is by using those vector types, that's float2 or float4, the compiler can identify that and automatically use packed instructions in those cases. So we are trying to reduce instructions. What matters for compute-bound kernels is where you have staged your data. To be truly compute-bound, you really want to read from registers. And so always investigating and looking for opportunities to just save your data in registers and using them from registers is a good idea. In in CDNA architectures, all of our Instinct GPUs, we have special matrix multiplication units. Those are called the matrix cores that you should be able to make use of in certain matrix multiplication like calculations. You can make use of those. And we have a blog post about how to do that using compiler intrinsics built-ins. But in the most cases, the library ROCWMMA is going to expose that functionality for you. That's the easiest way to do that. Typically, the matrix cores are used by libraries like ROCblas. We don't typically write code for that, but in some special cases, we've seen that. So let's take a quick moment. I think I have so much to talk about, and I think I will run out of time, but I'm going to look at this code and see what do you think could be wrong here. Just one moment. So we expect a multiplication there, two multiplications here, and an addition, right? But what we see are a lot more instructions than we expected. And the things that I'm noticing are these conversion instructions. FP32 gets converted to FP64. Multiplication is happening in FP64, etc. Everything is in FP64. Only at the end, things get converted back to FP32 for the store. That's not what we want. So this is very basic optimization 101 sort of thing, but it is so easily missed by many. The use of floating point literals is literally all the change we need to make to get what we expect. So just the multiplication and the addition operations that we expected is what will happen. All we needed to do was add that floating point literal to all these floating point values that we gave. Otherwise, they are considered as FP64, and then everything happens in FP64 domain. So those were some tips for the compute-bound kernels. And finally, we are left with the more complicated latency-bound cases. When we are latency-bound, we're waiting for something or the other. So some of the main ideas are, let's make sure that the device is completely utilized. Let's make sure that we're not waiting on unnecessary synchronization barriers, and we'll discuss that in more detail. Inside the kernel, when a wavefront is operating in lockstep, if there is divergence, that is, if we have written code such that some threads have to do one thing and some threads have to do something else, that can cause all of the threads have to go through all of the instructions anyway, so that just increases how much time we spend on such. So if we remove that, reduce or remove thread divergence, that can give us better performance in general. And then we also sometimes have to think about registers, how many registers we are using, and whether we are spilling. Spilling means we are writing to slower scratch memory, something like it is a part of HBM. And that takes several hundred cycles to spill and then to reload when we need them. So avoiding that can help us improve performance. So the case for increasing parallelism, right? The GPU has a lot of resources, and when we launch wavefronts can stall for many reasons. Maybe you're loading data and you're waiting for that data to come back to be ready for compute. Or you have a sync threads or something, and you're waiting there. So when one wavefront is waiting, you would like other wavefronts to keep moving. So that is why even the GPU is very good at switching to wavefronts that are ready to go. Maybe you have issued your load request. There are other wavefronts that can then issue their load request. So the GPU is good at identifying that and switching to those wavefronts that are ready to go. So what we need to ensure is that we launch a lot of wavefronts and hide the latencies of stalls. So we are going to take an example to discuss this concept called occupancy, right? What do we mean by occupancy? There is a limit of how many wavefronts we can have running at the same time on the device. And when we run our kernel, there is some number of resident wavefronts. So the ratio of the number of resident wavefronts to how much maximum we can have, that is called occupancy. Now, let's take this MI210 GPU as an example. We have 104 compute units. And in each compute unit, we can have up to 32 wavefronts. And that gives us a maximum of 3,328 wavefronts. When we launch our kernel, we want to think about, okay, do I have enough wavefronts to use all of the CUs? And do I have enough wavefronts to allow the GPU to switch when needed so that those latencies can be hidden, latencies of maybe waiting for the data to load, etc., right? So that is what we typically aim for, higher occupancy, but that is not always, in most cases that helps. In some cases, lower occupancy can be sufficient to saturate your hardware components. But in general, higher occupancy is good. So in this example, we're doing a DAXP. A DAXP of arrays of length, 1 million elements. You can do that in many different ways. You can just launch one wave. And if you launch one wave with 64 work items, you just loop over all the elements and you get the work done. Yes, but it takes time because you're not exposing parallelism. Here is one CU. In a GPU, there are many CUs, right? Compute units. And this wave gets launched to this one CU. This one thing is important to remember. All the wavefronts of a work group will be launched to the same compute unit because the LDS is shared and they all can use LDS to communicate with each other, right? And so, okay, if you launch, let's say 256 work items, that means 4 waves of 64 work items each. But one work group, that entire work group has to be launched to the same CU. So 4 waves are launched to this CU, and you get slightly better parallelism, but not, you are still leaving the rest of the GPU wide open with nothing to do. In the same thing, if you had completely assigned one thread to work on each element of the array, then you'll have thousands of waves, and you can fill up the GPU with all of them. You're hiding most latencies, and you're getting the work done in the fastest possible way. So this is exactly the progression of steps that we will do in the exercises after the talk. This is a very simple example, but it is very illustrative. But then not always. You may have 1,000 waves, but only some get scheduled. And why is that? That's because this compute unit has some resources that are shared between all the waves, and you can only launch as many as the resources will allow. And what those resources are, the LDS, which is here, which is common. You see that there are 4 SIMD, 16 wide SIMD units in each compute unit. Those are the ones that do the actual compute. Those are the arithmetic logic units. Each SIMD unit is associated with a vector register file. So the vector register size, file size, and then the LDS size, and the scalar register file size, those determine how many waves can actually be scheduled. So let's take a quick look at each one. LDS, you know what shared memory is. That's where we can stage data for faster access and so on. But in MI200 and MI300 GPUs, we have 64 kilobytes of LDS available. Now, this 64, let's say kilobytes, let's just keep it kilobytes. In 64 kilobytes, you've got to accommodate. It is being shared by all the work groups. Now, depending on your work group size, we are going to, and depending on how much LDS is required by each work group, we will be able to schedule that many work groups. So in this example, if your work group does not, if your kernel doesn't use any LDS, LDS is not going to limit your occupancy. If each work group is using 8 kilobytes, then only 8 work groups can fit in that CU, right? Even though there is room for 32, we can only fit 8. If you require a lot of LDS, in some cases that is an optimization, right? But in that case, only one work group can fit in the CU. So in some cases, having that work group be large enough can also work, but there are other considerations. When it comes to vector registers, we have a maximum of 512 vector VGPRs of size 4 bytes. So it is a limited size file. So if each wave is going to use less than or equal to 62 registers, then 8 waves per SIMD or 32 waves per CU, the full occupancy can be accomplished. But if you need to, it is an optimization to stage things into registers. Sometimes you may need more registers. In that case, that will limit how many waves can run simultaneously. That will limit your occupancy. This occupancy per SIMD is what you will see in the compiler and the profiler report. So don't get confused. If you get 8 in the compiler report, that is actually full occupancy. Okay, in scalar registers, typically one value, if there is a value, let's say something that's coming in your arguments that is common to all the work items of the wavefront, then those things will reside in scalar registers. Again, we have a limited scalar register size, and that will limit. But this is something that typically you don't have to worry about. In the case of very large constants arrays and things, I think you will try to copy them. If scalar registers can fit those, the compiler will make use of those, but otherwise it's just going to use the scalar registers for the arguments that you pass in. Register spilling. So if all the register allocation is done by the compiler at compilation time, when too many registers are required, the compiler may decide to go and write the data, some of the data, into slower scratch memory. because it's slower, the kernel takes longer. It's just better to avoid spilling in most cases. So when you write your kernel, if it is slow, get that compiler report and see how many registers are being used and check if there is any scratch usage. Then we want to think about how to reduce that. One of the very first things that we do is, by default, the compiler assumes that work groups are going to have 1,024 work items, and it allocates registers accordingly. Only few registers per work group, per wave. So if you know that your kernel only is going to be launched with, let's say, a work group of size 256 threads, then we can tell the compiler using launch bounds that, hey, you are allowed to use more registers in this case. Don't think that you're restricted. So that will help improve the performance of your kernel. It's just one directive that we add on top of each one of our kernels. It's always a good idea. Sometimes we may be spilling SGPRs to VGPRs, and then, it's something that we don't want you to stress about. It is just there for you to know of. And we have a very good blog post on this register pressure issue that dives deep with a couple of examples. Very good read. A lot of optimization tips there. This is what we discussed in the Mattermost channel earlier. So when the device is completely idle and we launch a kernel, it takes some time, because the hardware components, there are a lot of pieces that need to get up and get ready. So it takes a while for those waves to be scheduled. Once waves start being scheduled, then again, it can also take a little time for the entire device to fill, because scheduling waves, there is an algorithm for that. So that's what we call as the cold launch latency. And to avoid that, we always try to do a warm-up kernel launch before we start the timing region. And in our examples, you'll see most of our examples will have this particular methodology. In our figure of merit, we don't want this cold launch latency, definitely. Hot launch latency. The device is busy and you are able to launch, but in case you have very, very small kernels, this is something to think about. Let's say you are launching all the kernels in the same heap stream. The stream semantics say that all the kernel launches in a stream have to be ordered. Therefore, what that means is no wave in the subsequent kernel can be launched or scheduled until all of the waves of the previous kernel have completed. Now, when the kernel completes at the kernel boundary, there are some things that have to happen, certain flushes, so all the writes from your kernel have to be flushed out to HBM. Those happen at kernel boundaries. Why? Because any work done at in a GPU kernel then later has to be made visible to the CPU. System scope flushing is happening. Not at kernel boundaries, but at synchronization barriers if you had one. But at kernel boundaries, things have to be flushed to the L2. That takes cycles. So some things to remember: if you have very short kernels, it's better to you may suffer from kernel launch overhead. Again, not a big thing, but keep in mind. Okay, so in some cases, we may want to fuse kernels. The main reason is to avoid the launch latencies. Instead of launching multiple kernels, you launch fewer. And in this case, we also benefit from fewer data movement here. If you notice, we are reading A, we are reading B, and we're writing to C in the first kernel. And then in the second kernel, we're reading A, reading B, and reading from C, and then writing back to C. If you fused all of them, you just avoid this the whole index calculation the second time, and the reads. You just do the reads one time, and then you're ready to write one time. So you're reducing data movement, you're amortizing on the cost of that index calculation. And in general, for your larger cases, workloads, it must be beneficial. In some cases, you may have to split your kernel because if you're using too many registers. That's another thing we're not talking about here, but something to keep in mind. So synchronization is when you have a very large work group. If you have a sync threads, that's going to take some time. So it's expensive. So you may want to think about smaller work groups in those cases. Your algorithm may require that sync threads, but maybe you don't need to work with a 1024 thread work group. And host side synchronization can be an unwanted effect if you have a whole loop going on with asynchronous copies and compute kernels being launched. You do not want a hip malloc, for example, to be somewhere in between, causing the entire device to be synchronized before that hip malloc call can happen. So look for those kind of things. Profiling tools can help you with that in identifying those problems. And then, of course, if you're having asynchronous memory copies, make sure you do that with pinned host buffers. That way you can also overlap copies with compute. Atomics in MI200 to get the benefit of hardware atomics for FP64 data, we have to compile with a particular compiler option. It's M unsafe FP atomics, but on MI300 we do not need that. In general, the tip here is that reducing contention in atomic operations, like how many threads are doing the atomics at the same time, if you reduce that, that can help improve performance. Now on MI300 GPUs, we have multiple XCDs, and each XCD has an L2 cache that is local. So in MI200, L2 was our coherence point. But in MI300 GPUs, we cannot have the coherence station as the L2 as the coherence station. We have what is called an infinity cache, that is the last level cache, which is common to all the XCDs, and that is where we can do atomics. So that's something to know. There will be little extra latency when you perform atomics in MI300 GPUs. Thread divergence. If you have some threads doing one thing and other threads doing the other, then the all the instructions have to be executed, but each time some threads will be masked off. It may be better to do something smart where you avoid divergence. In this example, even in odd threads do something different, but if you were to have each thread just load 2 values and work with 2 elements, then you can completely avoid the divergence and you're just doing twice the amount of work in each thread. And you can stage in LDS data, but if you're able to keep the data in registers, and if you're working with just one wave in your work group, then you can use warp shuffle instructions to exchange data between threads in a wavefront. So there's a lot of material out there about warp shuffle intrinsics. So in summary, we have rewrite kernels that may be limited by different things, mainly memory bandwidth, maybe compute resources, maybe latencies. It's important to be aware of those and apply the right technique for the type of kernel that you're dealing with. Reducing data movement becomes very important for memory-bound kernels. Avoiding unnecessary compute and using some tricks like intrinsics and can help you minimize the number of instructions that you have to execute. And of course, having an eye on occupancy and whether we are filling up the resources that are available in the GPU can help us improve performance in most cases. It's just so much fun. I hope you are able to have the same kind of fun when you're working on kernels. It may seem complicated, but it is a lot of fun. On the MI300A architecture, there are some things that we'd like you to have in mind. There are no page migrations. GPU and CPU are sharing the same physical memory, so one allocation is sufficient. The choice of allocator can affect latency of first touch. So where you've allocated, let's say you have allocated using the device memory allocator. What happens when you use hip malloc is that the device page tables are populated. And when the CPU touches that piece of memory, those page tables on the CPU side are populated only on first touch. So there may be a latency that is visible there. When you use hip host malloc, when you allocate pinned memory, either of these methods, page tables are populated on both CPU and the device. So there should be no first touch latency on either side. When you use a system allocator such as malloc, then your CPU page table is populated, but the GPU only registers those pages at first touch. So tomorrow in the OmniPerf OmniTrace talk, you're going to see an example of this, and it's very fascinating. Page size will matter. The GPU prefers 2 megabyte pages because of the size of the translation look-aside buffer. So when you use system allocators, the page sizes are very small, and the TLB, the entries in the TLB have to be constantly loaded and reloaded because you cannot fit so many small pages, information about so many small pages. And so we recommend using hipmalloc for everything to guarantee the larger pages and to have lower first touch latency from your GPU kernels. And then, of course, APU opens up a whole lot of opportunities. For example, for copies, there are multiple ways to do copies. You can use SDMA engines, or you can use kernels to do the copy. You may want to do the copy on the CPU now using multiple threads and so on. So some interesting things that open up for us there. And that's the end of my talk. Thank you. I know I've gone a little bit over. But let's go through the exercises. I want to pull that up. Okay, so in the HPC training examples repo, you have a directory called hip optimizations. And inside that, we have this DAXP example. And all the code is already written. You can look at the differences between the codes. We are solving the DAXP problem. It's described here. Just do a make to build it on your system, and then run each one, and you will see that each one performs differently as we go along. There is improvement in performance, and the things that we would like you to think about and experiment with. So it's all out there. If you have any questions, I'm going to be available. All of us are here in the Mattermost chat. If you have any questions here, I can answer those as well.
Thanks for the presentation. I think it's like just only 5 minutes until 5. So yeah, people, they want to do some exercise, or they want to call it a day, so they are free. Well, thank you everyone for attending the training hour. Thank you, Gina, for presenting this last talk of the day. It has been very interesting. Tomorrow we will start at 1 p.m. UK time. I guess that we will use Zoom link, but I will confirm that on Mattermost. Have a nice rest of the day, and yeah, see you tomorrow.
Thank you, everyone. See you tomorrow.